In this video, we're going to do amount of substance, determination of formula. Now, we're going to go over empirical formula and molecular formula and how they relate to each other. And then we're going to go over 3 levels of calculations to do with empirical formula. And we're also going to do water of crystallization calculations. Now, molecular formula, it's really important that you understand the difference between molecular formula and empirical formula. So molecular formula is just the number of atoms in each element present in a molecule. So the number of atoms of each element. So it's very, very simple in terms of how it's presented. So let's look at a displayed formula of this compound, which is hexene. So you've got a double bond, and this is an alkene called hexene. Now, if you want to do the molecular formula, all you have to do is go along, and this is where a lot of students make mistakes, so do it slowly, and just count the number of elements as you go across. And you can see that there are 6 carbons, and hopefully you're looking at the video and counting them yourself right now. And then if you go along the outside, you can count that there are 12 hydrogens. You can also know that through the fact that if you've done alkenes, you know that alkenes' actual general formula is CnH2n. So if I know the number of carbons, I will know the number of hydrogens, because the number of hydrogens is 2 times the number of carbons in alkenes. But if you don't know the general formula of something, you really should count. So that means the molecular formula is just the number of carbons and the number of hydrogens in there. So it's C6H12. So that's our molecular formula of hex-1ene here. Now, how does that relate to the empirical formula? The empirical formula is the simplest whole number ratio of atoms of each element present in a compound. Again, what does that mean? All right. So the really important thing is it's a whole number ratio. So it must be a whole number. Okay, and it's the simplest. So it must be reduced down to 1 in relation to another number. Okay, so let's look again at hex-1ene. So hex-1ene's molecular formula was C6H12. And then if you go across and you say, right, okay, what is the simplest ratio between those 2 elements? Well, the simplest ratio between those two elements is actually 1 to 2. So 1 to 2. Okay, so that empirical formula of this is CH2, but the molecular formula of this is C6H12. So they're quite different. Now, sometimes, though, they can be one and the same thing. For example, in CO2, the simplest ratio of atoms to each other is 1 to 2 in CO2. It won't be different. But in a lot of molecules, they are different. Now we're going to go on to calculating empirical formula. And there are 3 types of questions we're going to go over. We're going to go over calculating the empirical formula from percentages, then from masses, and then we're going to calculate the empirical formula to the compare the empirical formula to relative molecular mass to determine the molecular formula. But we'll explain that later on when we do it. But let's start with calculating empirical formula from percentages. So a common question, and this can often be found as an MCQ in your second year of A-levels, is a compound of scandium, atomic number 45, has the following composition by mass. And so it gives you percentages. And those percentages should, if the question's done right, add up to 100%. So because they add up to 100%, you can treat these almost like a mass. So you can say 19.48 grams, 18.18 grams, because it's a percentage. Now, this question wants you to determine the empirical formula of the compound. So our exam tip here is going to be, and this is really important, so we'll leave it up as we do the question. When determining the ratio of the moles, if it is less than 0.1 from a whole number, you can generally round down. So if it's, for example, 2.09, you can generally round down. But if it's above 0.1, maybe for example 0.2 or something like that, then you generally have to times the whole number, times that number by a whole number to make the 0.2, for example, into a whole number. And again, it doesn't really make much sense when I talk through it, but it will make sense when I go through the examples. So again, as we normally do, let's push that to the right. Now, as we push that to the right, we highlight again our atomic number that's given in the questions. They've been very kind to give the atomic number of that. We This means you'll be expected to find the nitrogen and the oxygen on your periodic table. And we've highlighted all the percentages that we need. Now I'll talk about these two exam tips and leave them down there as I go along. So first of all, you need to do empirical formula questions in steps. So the first step is to convert to moles. Okay, so we are going to convert to moles now. So if that is the case, it's good to have a little table. So what we can do, and I really would recommend you do this every single time. So let's do scandium. Okay, and we know we have nitrogen, and we know we also have oxygen. So we've got scandium, nitrogen, and oxygen. We know we've got percentages of each, 19.48 for the scandium. Okay, and remember, because it is a percentage, we can use that as a mass. So we can convert that directly to a mass. And if you know the equation, it's moles equals mass over mR. So therefore, if I'm going to work out the number of moles, which is what I want to do here, okay, I need mass over mR. So my mass is going to be 19.48, and I've converted it into grams, okay, and then I divide that by its atomic mass, which is 45, which was given in the question. And then I go to the nitrogen. The nitrogen in that case is 18.18 grams. Now I divide it by its mass, which is 14. We then go to oxygen, and we know we've got 62.34 grams, and then we'll divide that by 16. Really important thing, and the common question, the common way these things are got wrong is that people know that nitrogen is N2 when it's an element, so sometimes they put in 28 for that and times it by 2. No, it's the element itself, it's not the molecule, so it's the element itself. So never put a number down here that means you've times any of these by anything at the start. So as we do that and we put that in, we are doing our moles at the moment. Okay, that will convert into numbers. So therefore, if we go and, then we can divide by the smallest number to give a ratio. So if we go to 0.4328, and that is the number in the calculator from this, 19.48 divided by 45. And then we go to 1.2985. Again, the little dots are just saying this is a long number in your calculator, and keep it in your calculator. Okay, and then from there we have 3.89625 for the last one, 3.89625. So we've got a number of moles of each of those. We've calculated that by looking mass over atomic mass. We now need to give the smallest number, divide by the smallest number to give the ratio. Smallest number is 0.4328. You can see from there and from there, this is the smallest number. So we divide by the smallest number to give a ratio. And hopefully if you do maths, you should be very used to this kind of thing. So I'm going to divide all of them by 0.4328. Okay, and if that's the case, we're going to start to get a ratio. And after we get the ratio, we can multiply to give a whole number if we don't have a whole number. So let's look at that ratio. So that ratio will be 1, and that ratio for here will be 3, and that ratio for here will be 9. Okay, so we've got 1, 3, and 9. And this is often where the mistake happens. The mistake happens that people think they finish the question by doing 1, 3, and 9. No, if you want to make sure that this is actually a good answer and it gets all of the marks, you've got to apply it to the elements. This is why it's really good to do a table like this. Now it happens in this question that we don't need to multiply to give a whole number because they're a whole number already. So it makes complete sense. We just don't need to do this last step, but we will do it in another example. So the final answer to this is to apply it. So we've got SC, N, and O. So that means we've got SC 1, N 3, 609. Okay? So the important thing here is to say, well, that's the empirical formula, but sometimes they complicate the question and say, well, what is the actual formula? And this is just asking you to have a little bit of intuition really more than anything else. So if you look at this, is there any ion that you recognise that might have 3 N's and 9 O's, or the ratio might be 1 to 3, so the ratio is 1 to 3. There's an ion which has nitrogen 1 to 3. Okay, hopefully you've thought about that now. Well, that ion is nitrate, so actually what we can have is we can say the actual formula of this is ScNO3. Okay, we've got 9 of them, so therefore brackets and 3. So this question is, we have got a proper chemical formula of it of ScNO33. We've got an empirical formula of ScN3O9, which would be perfectly good to answer. Okay, and that is how you use percentages to work out the empirical formula for a compound. We're now going to move on to doing empirical formula where we have to multiply to gain a whole number. So the question we're going to look at is for a compound of vanadium having the following composition by mass. Okay, so we can see we've got our numbers which we are directly going to turn into grams. Now we want to determine the empirical formula of the compound. So let's move this over to the right again. Now with that over to the right, if you remember from our previous slide, we've got 3 points. We want to convert it to moles, we want to divide by the smallest number to give a ratio, and then we want to multiply to give a whole number. This one we're going to have to multiply to give a whole number. And this is when this exam tip down here comes into play. Okay, when you determine the ratio of moles, if it's less than 0.1 from a whole number, you simply round to that whole number. So if it's 3.09, for example, you just round that down to the whole number. If it's above 0.1, you're going to have to find a whole number to multiply it by to make it into a whole number. We'll give you an example here. So what we do is exactly the same as we've done in the previous one, but this time we've got vanadium and we've got oxygen. So if we put vanadium here and we put oxygen here, we then convert to moles. If you remember, we convert to moles by mass over atomic mass. So the mass we've got here is, if we go over here in our orange, we've got 56 and 44, and therefore convert that directly to grams because it's a percentage by mass, and that means we can just go 56 and we divide by the atomic mass of vanadium, which is 50.9. We then go to oxygen, we've got 44, and we go 44 and we divide that by the atomic mass of oxygen, which hopefully you'll know is 16. So once we've done both of these, that will turn into a number. So if we look here, this is 1.1, okay? And then we look at this number, and this number is 2.75. And again, I encourage you, whenever you're looking at these videos, is that you look at them and try and do the calculation at the same time. So the next step is to divide by the smallest number to give a ratio. The smallest number is 1.1. So we'll do 1.1 divided by 1.1 equals 1. And there's our first part of our ratio. And then we do 2.75 divided by 1.1. Okay, now that will equal 2.5. Okay, so 2.5. So this is the problem. You then go to your exam tip, and in your exam tip, if it is above 0.1 or 0.5 is above 0.1, so 0.5 is above, okay, then you have to multiply the moles of each element to achieve the whole number. So if you want to turn 2.5 into a whole number, and think about this now, you will turn the 2.5 into 5. Okay, so that means I will do all of this, I will times by 2. Okay, so I'll times that by 2. That will turn it into a whole number. So if that is then times by 2, that means we can put in our numbers. So we can say, right, okay, that means we've got V and then 1 times 2 is 2. Okay, and then we take the 2.5 and times by 2, 2.5 times by 2, and we get V2O5. Okay, so if we just go through that again, we're going to work out our moles, we're going to turn the percentage into mass, divide it by the atomic mass of the element. Make sure we do this table again, it makes it really clear, it makes it really simple. We then divide by the smallest number. Okay, we didn't get a whole number. The number was above 0.1, it was 0.5. Okay, and then we figure out and we think, how can we turn that 0.5 into a whole number? Well, the easiest way is to times it by 2. Okay, so we times it by 2 on each one. That gives us a 2 and it gives us a 5. We then apply that to our formula, and therefore we have the empirical formula when you have to multiply to gain a whole number. The next example is going to be without percentages and straight from masses. It's actually a slightly easier question. So a scientist prepared the acid and they analysed the sample and gave some data. They want you to calculate the empirical formula, and here is your data. So you notice in your data right here that you have grams already, which means that you can turn those grams directly into moles. So you follow exactly the same process as you did before. Let's get rid of that over to the right again. Okay, and then let's start showing you how to do the question. So we've got moles. So we'll put our table as we normally put our table in, and then we start putting in our moles. So our moles is going to be our mass divided by our atomic mass. And that gives you your number of moles here. If we go across and we do exactly the same thing, we can see our mass here is then divided by our atomic mass. And then we do the final one, and we get our moles going all the way across. Exactly the same as what we've done before. Our next step, which hopefully you're remembering, is to get a ratio. So the ratio is going to be divided by the smallest number. The smallest number is this number here. Okay, so therefore we're dividing by it. We get 2.01. That goes back to our exam tip, where if it's under 0.1, you generally just round down. And this is under 0.1, so therefore it's rounded just down to 2. And we do that same process as we go across. We've got our 1 and we've got our 3, using that same rule. If it's below 0.1, then you round down. If that's the case, all we do then is just apply this to the elements. So, because they are whole numbers. So therefore H2SO3. And that is how you just do it straight from masses. We're now going to move on to water of crystallisation, which is a very common exam question. And water of crystallisation is to do with hydrated salts, where water is part of that crystalline structure. And the water bonded is called the water of crystallisation. So the most common example of using this, water of crystallisation, is with copper sulfate. So if you look at copper sulfate here, we can see that it's had water added to it. Now, this dot that you can see right here is denoting the water of crystallisation. It's saying that this water is bonded to this copper sulfate, or this salt. Now that is via a dative covalent bond if you've done it already, okay, in your bonding part of your course. Okay, but you don't really need to know anything more than that. You just need to know that the dot means that the water is bonded to the copper sulfate. Now, if the water is not bonded, we refer to it as anhydrous. And anhydrous copper sulfate, as you can see with the colours, is a kind of white colour. And you'll see it in your lab all the time. Because when you do practicals, teachers always use copper sulfate. Now, hydrated copper sulfate is the blue colour, and you'll hopefully make crystals of these. These crystals that you see in this picture were made in the lab at the school. Okay, and you can see they're beautiful large crystals of copper sulfate. Now from there, if you know the water of crystallisation is the water that is bonded, you can use it to calculate the ratio. So the ratio here, if you look, is 1 copper sulfate to 5 waters. And you can see the ratio here in the balanced equation again. So it's 1 to 5. So calculating this ratio is where the exams are going to ask you questions. So let's look at a couple of example questions on this. The student carries out an experiment, this time with iron sulfate, and they intend to remove the water by heating the hydrated salt. Diagram, usually given like this, okay, is where you have a crucible, and in the crucible you will have your hydrated salt, okay, and then you will put it inside a pipe clay triangle, which is here, and then that's on a tripod, and then you'll have heat coming underneath from a Bunsen burner. You'll often have a lid across the top as well. Now, the process for that is the student adding the hydrated salt to the crucible and weighs the crucible and the contents. Okay, so it weighs the crucible and the contents. Then it heats the crucible and contents and allows them to cool. And then the student weighs the crucible and residue, then repeats step 2 and 3 until the mass stays the same. Now, before they've done this whole process, they also would have weighed the crucible without anything in it. So they'd know the mass of the crucible without anything in it. So let's look at some of that data. So we've got our mass of our crucible, we've got a mass of the crucible plus the hydrated salt, and then we heated it. And when we heated it, we removed the water of crystallization. That's the important thing. The water is being evaporated off, okay, and it just leaves the salt behind. So that residue that we look at there will be just iron sulfate on its own, no water bonded to it whatsoever. So if you look at these two bits of data, you see the difference in mass between the crucible and the hydrated salt and the crucible plus the residue after heating. That will be our mass of water that has been driven off. The difference between the crucible and the hydrated salt and the mass of the crucible, that will be our mass of our salt. So if we've got the mass of our salt and we've got the mass of our water, we can work out moles of each of those and compare, which is how we get our ratio. But before that, I'd like to focus on step 3. So when we look at step 3, which we've highlighted here, this is a very, very common exam question. The student weighs the crucible and residue and then repeats step 2 and 3 until the mass remains the same. Why do they do that? Okay, that's the question. Why do they repeat that step 3? Well, the exam answer, okay, is basically that this is to ensure that all of the water of crystallization has been removed. So that means all of that water must be gone, okay, and you only leave the salt behind. So make sure you understand and know the answer to that question. So let's get on with doing the main part of the water of crystallization question. This is where you take the data to produce the ratio between the water and the salt. So the question itself is calculate the value of X in the formula FeSO4.xH2O. So you have to determine what X is. You do that by first of all working out the mass of the individual parts. So you want the mass of the salt, the FeSO4, and the mass of the water. If you have the mass of both of those, you can then work out the moles. Okay, and you can also work out the whole number ratio. And once you've got the ratio, you have the number of waters compared to the number of moles of your salt. So let's start to do the question. So it's this X we want, okay, and we want it of the individual parts. So we want it of the FeSO4 and the H2O. Now, we've just highlighted down here our data, and you can see that the mass of the crucible plus the residue after heating, and we've worded it in that way because that's how they'll word it in the exam. Okay, and that is the mass of the crucible plus the FeSO4 with all the water driven off. You've heated it, you've got rid of all of the water. Okay, so if we want to know how much FeSO4 there is, we need to take the mass of the crucible away from the mass of the crucible plus the residue. Then we'll have the residue remaining. So what we can do is when we're calculating the mass here, we can say it's 16.474, okay, and we can minus 15.12. Okay, if we minus 15.12 from 16.474, that'll be equal to 1.354. Okay, so 1.354. And that will be in grams. Okay, we do the water, and that's the next part, and we'll see we're changing our highlighting down here, and this time we're highlighting the mass of the crucible plus the hydrated salt and the mass of the crucible plus the residue. The difference between these two numbers is that hydration, is the water. Okay, so if we want to work out the mass of the water, we take these two and we say, right, 17.599, okay, and we minus 16.474. 16.474. Now that will equal, okay, 1.125 grams. So we have 1.354 grams of the salt, 1.125 grams of the water. Now we need to go on to the number of moles. So if we take the 1.354 and we'll divide that by the mass of this. Now the mass of this is 51.9. Okay, and when you divide that in, you get 8.913. Okay, so 8.913 times 10 to the minus 3. We then go on to the water, and we go on to the water, that will be 1.125 grams, and that will be divided by 18, and you'll get from that 0.0625. Okay, so we have moles now. So this is moles, okay, and this is moles. Okay, we can now move from that to getting a whole number ratio. Okay, so what we do to get our final answer is basically take these two numbers, and we've got 8.913 times 10 to the minus 3, which is a smaller number, and we expect the FeSO4 at all times to be 1, or the lowest number. So basically that has got to be 1, and the water will be greater than 1. So what we do is we take 0.0625, okay, and we will divide that, okay, by this number. And that means we find out how much bigger the 0.0625 is. So 8.913 times 10 to the minus 3. And that will equal, if we've done our maths properly, that will equal 7. Okay? So if we're going to put the formula of this down right now, we can then apply that to the equation and then go, this is FeSO4 dot, and it will be 7H2O. And we have determined at that point our water of crystallization when it comes to hydrated iron 2 sulfate. Our last example is of water of crystallization, but by using percentage by mass. So when used as a drying agent, sodium sulfate becomes hydrated. And you can see here our water of crystallization is denoted by the dot and then the XH2O. And again, you've got to work out what X is. The hydrated salt contains 47% by mass. And this is the difference between the other question, is you're just given one bit of data and that's it. And you're not given all the data from the experiment. Just 47% by mass of water of crystallization. You've got to calculate the X in there. So let's again move that over to the right. So as it moves over to the right, we just highlighted the key parts. The key parts is 47% and by mass. That means it's a percentage by mass of the whole thing, which means you can take the percentages and turn them into a mass. So if you've got a mass, you can work out moles. So we can just do moles and then do our whole number ratio. So if we do that, we can say, right, and we've got the sodium sulfate. So here we'll have the sodium sulfate again, and then we'll have the H2O. And then look across, we've got 47. So that means 47% the water of crystallization. That means here, so we've got 47, and we're going to divide that by 18 because that's the molecular mass of water. Then we're going to take the remaining, because this is a percentage, so that's 53. Okay, and we're going to divide that 53 by the molecular mass of the sodium sulfate. So I'm going to do that quickly for you, but if you want, you can pause the video and work it out yourself. okay, and that will be 142.1. So we've got 142.1, 53 divided by the molecular mass of the sodium sulfate. Now from that point, we then work out what the number of moles are. So the moles of the water is 2.61 when you put this into a calculator, okay, and that is a number you should keep in your calculator. If I ever do 3 dots after something, it means it's a very long number, and just keep it in your calculator. We then do the sodium sulfate, and the sodium sulfate turns out to be 0.372, and again, dot, 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 and that is also a number of moles. So we now have our moles, and we have our moles of water as well. So we can now find out the ratio. So the ratio would be, again, take the largest number, which is 2.61, okay, and it'll be 2.61 dot divided by 0.372. And when we do that, that will equal the number 7 again. So it happens that the answer to this question is exactly the same as the answer to the previous one if you've been watching all the way through the video. Just to go through that again, because it is a mass, percentage by mass, you can convert that number straight into grams. So here we can convert it into grams, and if we want to make that a bit more obvious, put the G there. Okay, and then we are dividing it by the molecular mass. That works out our moles. Our moles are here. We now know the moles of each of them, so we can do a ratio. Take the largest number, divide it by the smallest number, and we should get the number 7. That means if we're doing the final formula, it'll be Na2SO4 dot, okay, and then it will be 7, and then we've got H2O. And that is how you work out the empirical formula when you're just given the percentage by mass for the water of crystallization.